look at the notes. Physical properties of carboxylic acids. They have higher boiling points than alkanes and alcohols because of the stronger intermolecular hydrogen bonds. It is stronger because the OH bond is more polarized. Okay, so if you compare alcohol, right, this is your typical kind of alcohol. We can see that you have an electron donating group here, right? While for carboxylic acids, you have an electron withdrawing carbonyl group here, right? It is electron withdrawing because O is electronegative. So this polarizes this bond more than this bond, right? Because for the one above, there's nothing but just a carbon. So for the bottom one, it's more polarized. So when you have more polarized, the delta minus and delta plus are greater. Hence, there's greater attraction, which is why your hydrogen bond is stronger. So larger alcohols have larger electron cloud, thus greater polarizability, stronger IDID forces, and higher boiling point. Right? I think I mean carboxylic acids and not alcohols, right? So larger carboxylic acids have larger electron cloud, thus greater polarizability, right? That's why your carboxylic acids gets progressively higher in terms of boiling and melting point. For solubility, carboxylic acids dimerize in the vapor state and in nonpolar solvents, right? It doesn't dimerize in water. Why doesn't it dimerize in water? Because it can form even more favorable hydrogen bonds with water, as shown on the right. Okay, the diagram on the right. Between each other, they can only form 2 hydrogen bonds, while you can form many more with water. So enthalpically, you will prefer to form hydrogen bonds with water if, let's say, it's the aqueous state. But if it exists in the vapor state or in the nonpolar solvents, right, you prefer to hydrogen bond to itself, to another of itself. So next, as the carbon chain grows longer, it gets more and more hydrophobic in character. This one I really emphasized many times. And if the carboxylic acid gets deprotonated, a carboxylic anion is formed which is soluble, right? That's why sometimes you see questions, they say that compound X with molecular formula C something, H something, O something, and then they tell you that it is soluble in sodium carbonate. You will know that most likely it's a carboxylic acid because phenols doesn't react with sodium carbonate. Okay, so you have your ROH, you have your phenol, and your RCOOH, right? And you should know which one reacts with what, right? So these are the 4 basic kind of reagents: sodium hydroxide, sodium bicarbonate, and sodium carbonate, right? So sodium will react with all 3, NaOH will only react with these 2, and the carbonate species will only react with your carboxylic acid, right? So if you were to read your question carefully, you should be able to deduce whether it's this or this, right? Depending on they dissolve in what, right? So now example 1, will carboxylic acids be more soluble in acidic or basic conditions? This is quite obvious, right? It's more soluble under basic conditions, right? So you can actually use your Le Chatelain's principle to explain. RCOH plus OH minus, right, to get RCOO minus plus H2O, right? You know that this is more soluble, right? So it makes sense to think that under basic conditions, these will increase, so position of equilibrium will shift to the right, so it gets more soluble, and vice versa, right? So under acidic conditions, it will be less soluble. This is quite straightforward. So next, acidity of carboxylic acids. Carboxylic acids are weak acids which dissociate partially, so think of the arrow, right? towards the left is longer because it's a weak acid. And the strength of an acid depends on the stability of its conjugate base. The more stable the conjugate base, the more acid it is. Right? We always compare the stability of the conjugate base when we want to compare acidity. Right? So the first step is always to draw the conjugate base and discuss about the stability. So for alcohols, after an alcohol dissociates, an alkoxide anion is formed. So the electron donating iron group will donate electron density. You intensify the negative charge. Therefore, the conjugate base is not stable. Therefore, it is only weakly acidic. Right? So you see the chain of thoughts. First is you always deprotonate, and then secondly talk about the stability of the conjugate base. Okay, always these two. Later on we'll see a more systematic way of comparing, right? So next for phenols or enols. After a phenol or enol dissociate, a phenoxide anion is formed. So first thing, I deprotonate it. So due to the overlap of the p orbitals of oxygen with the pi electron cloud of the benzene ring, negative charge is delocalized, making it more acidic. This one already explained in alcohols as well, right? So the resonance structures are as shown. For carboxylic acids, a carboxylic anion is formed after deprotonation. So due to the overlap of the p orbital of the oxygen with the p orbital of the carbon beside it, the negative charge can delocalize over the two highly electronegative oxygen atoms, right? So if you were to draw the bonding picture, right? This is your carboxylate. Everything is sp2 hybridized. This, and sometimes they argue that this oxygen is also sp2 hybridized. Sometimes they say that it's sp3, right? Just take note when you ask to, but you won't be asked, right? If you are asked about the hybridization state, just write sp3, right? So for now, I just assume that it is sp3 so that I don't confuse you. So this is your sp3 hybridized, this is your sp2, these are your two sp2 hybridized electron atoms, right? So you can see that after deprotonation you have a negative charge residing in your sp3 orbital. So what will happen is this, although it is slanted at 109.5 degrees, right, it can still overlap, although not as effectively as an sp2, with the adjacent carbon, right? And this negative charge can somehow be dispersed over this system because they are symmetrical, right? So this delocalization of negative charge disperses it and thereby therefore stabilizing the negative charge, right? If let's say you use sp2 to explain, it will also work, and it is preferred because now there's no such issue as some kind of symmetry restriction, right? Now if let's say you deprotonate your carboxylic acid, your negative charge will be lying in an unhybridized p orbital, right? Just now it's an sp3, now it's an unhybridized p orbital. So we know that unhybridized p orbitals, these three are parallel to each other, so the overlap is more effective, right? But either ways you will need to involve the concept of delocalization. Right, so compared to phenol, you see that for phenol you have negative charge delocalized over 6 carbon atoms. Right, we know that carbon is not electronegative compared to oxygen. While for carboxylic acids, the negative charge is delocalized over electronegative atoms. So therefore, this delocalization is more effective than your phenol. That's why your carboxylic acids is more stable, so it's more acidic. Okay. So if you can recall, last time we talked about the acidity of enols also. Sorry, not enol, carbonyl, right? Remember we talked about the alpha hydrogen, right? The concept is the same. After I lose this hydrogen, I'll have a negative charge on this carbon. So if I were to draw the bonding picture, right, everything is the same, just that I'm changing this to carbon. Okay, so same thing can occur. This negative charge can also overlap sideways, and get stabilized. So that's why we say that alpha hydrogens are acidic, just like your carboxylic acid. But of course, it's not as acidic as your carboxylic acids, because you deprotonate first and you compare stability of conjugate base. For this, the negative charge is delocalized over carbon and oxygen, but for this, it's delocalized over 2 oxygens. Therefore, your carboxylic acids are more acidic. Right? Same concept by using these two to explain. Right. So next, comparison of acidity. So as spoken above, acidity follows the following trend, right? Carboxylic acid greater than phenol, greater than water, and greater than alcohol. So if you compare the acidity of water versus alcohol, this is your water and this is alcohol. Like what we said, we always deprotonate them, right? So after deprotonation, we have these two species. For your carboxylic acid, it donates electron density, intensify a negative charge. But for water, no, right? Hydrogen is not really an electron donor. So therefore, this negative charge is intensified, hence is less acidic, right? The least acidic. So now as a form of practice, right? Which one you think is more acidic? This species or this species?
Second one.
This one?
Yeah.
You agree? Agree, huh? Okay. So now another question, right? Which one is the stronger base?
The first one.
You agree? The first one? So why the first one?
Because intensifies the negative charge. This is more likely to bond with hydrogen.
Yes. Okay. So you can actually use what we have learned to to talk about it, right? Another way you can think about it is, right? Why not you protonate them first and compare the acidity, right? You have learned in acid base that if I have HA, dissociate to become, I won't write the full equation, to become A minus, right? If this is weak acid, this one must be a strong base, correct? So just now you say that this one is a stronger, this one is a stronger acid, correct? Means that its base is a weaker base, which means this is a stronger base, right? This is another way you can explain by making use of your theories of acid and base, right? So either way is fine, right? So next, this table here, right? I already told you the answer just now, right? So you just take accordingly, right? Okay, yeah. Good. Next, some kind of ninja rules, I call it, right? That no other people, no other tutors or teachers will ever teach you, but it's very, very useful in predicting your acidity, basicity, nucleophility, leaving group ability, blah blah blah, right? So even when you go to uni or whatsoever, if you deal with higher levels of chemistry, this set of rules is still very, very important. You can explain a lot of things. And again, it's just for information, but it's very, very easy to understand, making use of what you have learned already, actually, right? So now, we are using these aerial rules to predict the stability of ions, which will help us understand the acidity of your acids, right? Because they are related. So, the comparison of acidity involves comparison of the relative stability of the conjugate base. Stable conjugate bases have higher acidity, right? This one already know. So in order to compare acidity, first we can look at the atom bearing the charge, right? So ignore the in the same row, in the same column first, right? We look at some examples, we'll learn by examples, right? So if the two atoms are from the same period, electronegativity is the dominating factor. And if the negative charge resides on an electronegative atom, it is attracted more strongly to the nuclei and more stable, therefore more acidic. Right? So if you compare butane and propanol, it should be obvious that propanol is more acidic, correct? This is because after you deprotonate, the negative charge is more stable on oxygen than on butane. Again, we are deprotonating first and then we compare the stability. Right? So this is for the same period. Okay? Let me see the next. Okay, so now as an example, can you try to compare the acidity of H2O versus NH3, right? Which one is more acidic? So it should be quite obvious, right? Which one have you ever not treat as an acid before? It will be ammonia, right? The reason is very simple. First step, deprotonate them. You have negative charge on O, negative charge on N. This is more stable because it's more electronegative, right? Quite simple. This is for the same period. Take note. If they are from the same group, right, size is the dominating factor. If the negative charge resides on a larger atom, the charge can be spread over a larger volume of space, hence a greater stabilization and acidity. This is rather similar to your benzene, right? For benzene, remember your for your phenoxide, remember your negative charge is dispersed over a large area, therefore it's stable. Same thing, if your atom is larger, it can also disperse over a larger area, a larger volume, therefore it's more stable. So if you compare water with H2S, right, smelly gas, you will find that H2S is actually more acidic because sulfur is greater, right? And that's why I put the two partial periodic table above, right? So in the same row, you will compare electronegativity, same column, compare size. Quite straightforward. Okay. Now this is the same for your HF, HCl, HBr, HI, right? You will know that HI is more acidic because you can say that the negative charge is dispersed over a larger area, right? Or some people say that because HI bond is weaker. But like what I said, if you say something like HI bond is weaker, it's true, but that is assuming you form radicals, correct? So it's not really that correct, although it can explain the phenomena here. Okay, this should be the correct explanation. That's the first factor, right? Quite straightforward. Next, resonance. Sometimes the negative charge resides on the same atom for both molecules and you cannot use the first method, right? So therefore we need to move on to the next approach of comparing the ability of the conjugate base to form resonance structures. For example, ethanol and acetic acid, which is your ethanoic acid, right? So if you deprotonate them, you realize that for both of them, the negative charge resides on oxygen. So you cannot use the first method. So now you need to compare resonance, right? It's quite obvious that this one can resonate, but this one can't. Which means this one will be more stable, hence more acidic, right? That's the ability of delocalization. Now what if both can delocalize? Then we'll look at the extent of delocalization, right? So if you want to compare the following example, although both molecules can form resonance stabilized conjugate bases, the phenoxide ion is more stable as the negative charge is dispersed over a larger number of atoms compared to the one on the right hand side, right? For the right hand side, it's dispersed over only 3 atoms. For the left hand side, it's dispersed over the whole ring, right? So therefore, phenoxide will be more stable and hence more acidic. And that is your resonance effect, right? And then we can move on to the third point, which is inductive effect. So sometimes, right, both of them have the same resonance structure and both of them lie on the same atom, then you must look at inductive effect, right? For example, your acetic acid and the right side, which is your trichloroacetic acid, right? So electronegative chlorine atoms will withdraw electron density via induction, therefore stabilizing a negative charge. This one is quite simple to understand. So it's obvious that the one on the right will be more acidic, right? In addition to the identity of the electronegative to the atom, the distance also matters, right? The closer it is, the more acidic it is, right? Same thing if it's a electron donating group. If it's a electron donating group, the closer it is, the least acidic it is, right? This is your inductive effect. And lastly is your orbital effect, right? Sometimes all the above three factors may not help, right? All of them are on the same atom, there's no resonance, or all of them have resonance and there's no inductive effect, right? For example, the one below here, the two hydrogens, you can see that both lie on carbon. There's no way for it to draw resonance structures, and there's no inductive effect because they are all carbon, right? So now you need to compare orbitals. So you can see that the hydrogens are on the okay. So if you deprotonate them, you can see that the negative charge on the left lies in the sp2 orbital, while the one on the right lies in the sp orbital, right? So if you can recall the shapes of your sp, sp2 and sp3, right, you can see that sp looks more like a s orbital, looks more spherical, and sp3 looks more like a p orbital, right? So for sp, which has a greater s character, right, the negative charge will be closer to the nucleus. We know that nucleus is positive, the negative charge is negative, so the closer they are, the greater the attraction and the greater the stability. So therefore, the atom on the right, the CH bond on the right, is more acidic than the one on the left. This is the orbital effect, right? So that's why it is called ARIO rule, atom resonance inductive orbital. So you can use this to compare a lot of things, right? This is the first time we have encountered ARIO, but it's not the last time, right? We're going to see again in the next chapter. So now you learn ARIO, so which one comes first? It's very simple. A comes first, R comes second, and so on, right? So you always consider the one above before you consider the one below, although there might be some variations, right? But it's quite rare. So this rule is very trustworthy, and if you use this rule to compare the acidity of your alcohol, water, phenoxide, it works as well, right? For example, I actually already given you the example, right, just now. So why not we try the following examples, right? Use the ARIO rule. And maybe you write at the side which rule have you determined, which one. Is it A or is it R or whatsoever. The first two should be quite straightforward, right? The first one is atom, the second one is resonance, right? Because for the second one, if you deprotonate this, right, this can delocalize into either this or this, right? But for this one, it can only delocalize into one. So the extent of delocalization is greater for this, therefore this is more acidic, right? And then for the last one, it is by orbital, right? So same thing, although I give it a negative charge, give it a positive charge, it still works, right? So first, I always deprotonate them. So after I deprotonate the first species, I'll have this, and if I deprotonate the second species, if I deprotonate the second species, I'll have this. So now, just now we are comparing the negative charge, right? But recall that negative charge is just the same as a lone pair. Correct. The negative charge is a lone pair. So now I can just compare the stability of the lone pair. Same thing, this lies in a sp2 orbital, this lies in a sp orbital. So the sp is more stable, therefore this is more acidic. Right? The negative charge is the lone pair. Remember. Right? So this has many applications. You can ignore the whatever your school has taught you, right? With this rule in mind, you can basically solve all those kind of acidity or basicity comparison kind of questions, right? We will see the basicity one for during the next chapter, right? So this is, of course, you can draw your own molecules and use this rule to compare, right? It works. So next, reactivity of your carboxylic acid derivatives. This part is just for information, right? Although carboxylic acid derivatives have the carbonyl CO functional group, they react very differently compared to your aldehydes and your ketones. For your aldehydes and ketones, they undergo nucleophilic addition reaction, but for carboxylic acid derivatives, they undergo nucleophilic substitution reaction, or we call it nucleophilic acyl substitution, right? Acyl stands for the CO group, right? From above, you should be able to rationalize that the reason behind their reactivity is because of X, because they differ in X. One is carbon, the other one can be chlorine, OR, or NR2, right? Why is it called nucleophilic substitution? Because something is kicked out and you have a nucleophile that's doing the attack, right? This one you should know how to classify, right? This one is in your syllabus, right? But the reactivity part is not. So if you were to look at this nucleophilic acyl substitution mechanism, you can see that the first step resembles something that I've learned, right? So can you tell me what's the thing that I've learned that resembles the first step? What's the mechanism that I've learned that looks like the first step?
SN2.
You sure it's SN2? That's a nucleophilic addition, isn't it? You have your carbonyl reacting with your Cn minus. The first step is the attack of your Cn minus to the carbonyl group, right? Which is the same as this. Okay? So the first step is actually just your nucleophilic attack, which is identical to your nucleophilic addition. Again, it is slow, right? Now what differs is the second step. After you form this tetrahedral intermediate, remember for your, you don't draw because it's on the right hand side, right? You can just refer to the right hand side, the mechanism, right? This mechanism. If you are looking at nucleophilic addition mechanism, which is the branch on top, you can see that the second step is just a protonation, right? That's your nucleophilic addition. But for your nucleophilic acyl substitution, the second step is not a acid-base reaction, but a kicking out of a nucleophile, which I will just call it a loss of a living group, right? So what actually happens is that this negative charge actually comes back down to form a double bond and kicks out X, right? So the question becomes, why does it like to kick out X instead of a protonation, right? Now this is explained below, right? So you can just listen to what I'm gonna say, right? We know that, let's say for carbonyl group, right? You have carbon-carbon, all the R groups, right? So after my nucleophilic attack, I will form this tetrahedral intermediate, right? So initially, my starting material, the bond angle is 120 degrees, correct? Everything is pretty far apart. There's not a lot of sterics because they are all facing away from each other. But as you form this tetrahedral intermediate, your bond angle becomes 109.5 degrees or lesser, depending on what is the R group. So there's actually an increase in steric hindrance, and the molecule do not like it. It likes to go back to 120 degrees, so that it's more sterically, less sterically crowded. But if let's say all of these are R groups, R, none of them likes to leave. So what will happen is this cannot kick any of the groups out. In order to stabilize itself, it can only perform a simple protonation to neutralize this negative charge. So now at least it's neutral. At least it's slightly more stable than the intermediate. Right? But now if let's say I have a chlorine here. Right? Same thing, originally I have 120 degrees. Right? After my nucleophile attacks, right, I form this tetrahedral intermediate. Right? So now it has got two choices. One is perform a simple kind of stabilization by just protonation, although I'm still sterically hindered. Another option is to kick out this Cl, right? Because once I kick this Cl out, I'll go back to this structure, which is more or less not sterically hindered compared to this, right? So therefore, you prefer to kick out the Cl in this case, but for the just now that case, you prefer to do a protonation. Can you understand, right? So that's why for this, it undergoes a whole different kind of mechanism compared to the first one. So now, the lesson learned from these two examples is that if let's say this group can leave very well, likes to be kicked out, you'll be kicked out. If it doesn't like to be kicked out, you will stay there and you'll just do a protonation, right? So in summary, I already stated here, if X is an unstable leaving group, for example, your alkyl, your H minus, or your C6H5 minus, all these are poor leaving groups, right? Because they don't have any electronegative atoms to hold the negative charge, right? Remember, if let's say you have an X species here, after this comes back down to kick this X out, right? By conservation of charge, right? This will be kicked out as this will become X minus. So it must be a species which can stabilize the negative charge, right? For the bottom branch, if X is a stable leaving group, for example your Cl minus, your Br minus, or your H2O, you can see that all these have one thing in common, is that they contain an electronegative atom, or atom that is large enough, right? Or an atom that can stabilize the negative charge, right? How do we compare how good they are at stabilizing a negative charge? Again, ARIO, right? We can see that this is another use of ARIO rules, right? So therefore, 1, 2, 3, 4, if you look at the fourth bullet point, for carboxylic acid derivatives, if X equals to OR, NR2, Cl, or CX3, if they are expelled, right, they are good leaving groups, right? So they are better at stabilizing a negative charge. You can use your aerial rules to explain. Therefore, the mechanism which dominates depends on the identity of X. If X is a poor leaving group, it will be a nucleophilic addition. If it's a good leaving group, it will be a nucleophilic acyl substitution, right? Just take note, for that bracket, right, I have a CX3, right? We have actually dealt with this CX3, right, before, in terms of CI3, right? Remember your iodoform reaction? We say that this one will slowly be replaced by iodine, and eventually what happens is that your OH minus will come in and perform a nucleophilic acyl substitution such that it becomes OH, and your CI3 is exactly this mechanism, right? And afterwards you will just perform a proton transfer, right? Or you can say acid base to get your CHI3 plus your carboxylate, right? This is your iodoform reaction, okay? And this mechanism, nucleophilic acyl substitution, this mechanism you are not required to know, right? This is just extension, right? So we can try example 3. Same thing, make use of the ARIO rule. And I'll demo A first, right? So for A, you have an ester and you have your amide, right? Remember, when you kick out the leaving group, right? The leaving group will eventually become O, this thing O minus, correct? Because we are kicking out this group. In other words, you can think of it as breaking this bond hydrolytically, right? And for this case, you will have this. So now you just have to compare which one is more stable using your ARIO rule, right? So by ARIO rule, A tells me that this is more electronegative, this is more stable, right? So this will be more likely to undergo the reaction, right? Because it's more stable. C is a bit tricky. For B, it will be the second one, right? Because if you compare hydroxide and water, one is neutral, one is charged. So of course the neutral species will be more likely to be kicked out, right? And then the tricky thing about part C is, although Br minus is a more stable leaving group, right? Now you will have to compare rate of your nucleophilate substitution, right? We know that chlorine is more electronegative than bromine. So this actually pulls your electron polarizes your bond more than this, right? So these will have a greater delta plus and these will have a smaller delta plus, right? So if this has a greater delta plus, the nucleophile will be more likely to attack this than this, right? And for this case, since these two factors that we've discussed opposes each other, right? Let's just assume that this factor is stronger, right? So that this is more reactive. Okay. And for the last one is just resonance, right? Because the one on the right can resonate, the one on the left can't, so the one on the right will be more stable. Okay, now let's look at the next part, preparation of your carboxylic acids. You can do so by strong oxidation of your primary alcohol or your aldehyde, both of which will give you your carboxylic acid. Or you can perform your oxidative cleavage, which will also give you your carboxylic acid, but take note that you can only perform oxidative cleavage to get carboxylic acid if it's this kind of alkene, right? For the other kinds, you'll either get carbon dioxide or a ketone. Okay? And for both of these, you will have your purple KMnO4 decolorized. Okay? So you can also obtain carboxylic acids, right? Some kind of aromatic carboxylic acids by side chain oxidation. So for the first one, you will get your carboxylic acid, okay? For the second one, you will get your benzoic acid plus your carbon dioxide. Take note that your carbon cannot be lost, like suddenly lost, right? Whatever that's to the right hand side will be lost, right? So for example, if you have this species, you cut here, this one will become your carbon dioxide, this will become your carboxylic acid. Okay? If let's say my carbon chain grows longer, same thing, I'll cut here. But now instead of becoming this carbon dioxide, right? Some people will say that I'll get 2 carbon dioxide, which is wrong. You should have a CH3COH, right? It doesn't become 2 carbon dioxide. So just take note. Now if let's say you have this kind of bicyclic kind of structure, you have 2 carboxylic acids and 1 carbon dioxide. Right, same idea. break here, right? So this one can only become carbon dioxide, right? Make sure not to draw the number of carbons wrongly. Okay, and then for the last one, there's no reaction. Remember, in order to have side chain oxidation, you must have at least one hydrogen connected here, right? So for the last one, there's no oxidation, right? This is another way you can get carboxylic acids. And just for information, we have learned about alkynes briefly, right? When we learn alkenes. So for alkynes, if I perform oxidative cleavage, right, what will I get? Let's say I have this alkyne, right? If I perform oxidative cleavage, what product will I get?
Get a carboxylic acid.
I'll get carboxylic acid plus carbon dioxide. Okay, this part will become my carbon dioxide and this part will become my COH. Okay, just take note. So acidic hydrolysis of nitrile will also give me my carboxylic acid, right? So make sure don't draw the number of carbon wrongly, right? A lot of people just forget the CN carbon, right? So acidic hydrolysis will afford this carboxylic acid, and remember your nitrogen containing product, right, which is your ammonium, NH4+, right? And for alkaline hydrolysis of nitrile, you just have to take away this H, right, and change this to ammonia, because the alkaline, the base will deprotonate this and this, right? Hydrolysis of your esters will also give you your carboxylic acids, right? So you have your RCOOH plus your ROH, right? Can you still remember which is the bond that's breaking? Is it A or is it B? A, not B. So just take, remember the 18 oxygen and 16 oxygen, that question, right? If you forget, please go refer. This is very important, right? Nowadays they like to ask deuterium, they like to ask isotope kind of questions, right? The mechanism is just for information, right? We already talked about the mechanism before. And next is the hydrolysis of your acyl halide or acyl chloride, right? You can actually hydrolyze them just by water. Later on we'll see why they are so reactive, right? So this is the mechanism. If you were to look at the mechanism, you can see that the first step is just a nucleophilic addition kind of mechanism, right? And for the second step, you see that Cl is being kicked out because Cl is a stable leaving group, as what we have discussed. So after Cl is kicked out, you have this kind of carboxylic acid kind of structure. So this Cl minus, which is a weak base, will deprotonate your carboxylic acid, right? So that it becomes a neutral species plus HCl, right? So now, how does the rate of hydrolysis compare to CH3Cl and C6H5Cl? Will it be faster or will it be slower? Faster or slower?
It's faster than CH3Cl, but slower than.
How about you? if I perform hydrolysis, means I'm using water to break the CCl bond, okay? Or I can use OH minus. It's also called hydrolysis. So for the first one, it is a SN2 kind of reaction, right? For this one, I'll need this to attack this species first, and for this, I'll need my OH minus to attack this carbon and to kick this Cl, right? So which of these three will be the least favored? Which one will it be? This one, okay? Because we have learned that there is partial double bond character because of the overlap, blah blah blah, right? So therefore, this is highly unfavorable and unlikely, right? And if you compare these two, right, for this case, this bond is polarized, yes. But for this case, right, you have this electronegative oxygen, right, and you have this Cl, both pulling the electron density from this carbon. But for this one, there's only a Cl. So therefore, this bond, this carbon has a greater partial positive charge. Or you can say that this is more electrophilic, right? So therefore, the rate of hydrolysis for this is greater, right? We'll see this again later, right? The concept for this is on the next page, right? So don't worry so much for now. So next, reactions of your carboxylic acids. First is your acid-base reaction. If you have your carboxylic acid, you can react with your sodium or NaOH to give hydrogen gas, right? Take note that for sodium, you only react with sodium will react with it to produce half a mole of H2 gas, right? Because we only have 1 H per hydroxylic acid, right? So we have the corresponding carboxylate, right? Trochloride plus your half a mole of H2. If it's NaOH, then it will be water, right? For acid base wise, the second one, right? If you react with your carbonate, this one you shouldn't have any problems balancing the equation, right? You have this plus of course your water, right? So you can go and balance it. Take note of the ammonia. If you react carboxylic acid with ammonia, is again an acid-base reaction, and what you will get is your ammonium carboxylate, right? Which is this. It's an acid-base reaction. They will not form amides, right? Please take note of that. And for the last one, it's carboxylic acid reacting with 2,4-DMPH, right? You should have learned that carboxylic acids do not react with 2,4-DMPH, correct? But that statement is actually somewhat untrue, right? Why do I say so? Recall that this is your 2,4-DMPH, right? I won't draw the other half, right? This is your 2,4-DMPH, okay? So just now we already said that your carboxylic acids react with your ammonia, right? Now if you were to look at this, isn't this an ammonia-like species, right? So by right it should also react, but they won't undergo condensation, they will only undergo acid-base. If they undergo acid-base, same thing. These will be protonated, right? And then you have your corresponding carboxylate. Okay. Now just a quick question. For 2,4-DMPH, right? There are lone pairs here and here, right? So theoretically, this one can also act as a base because it has got a lone pair. So why isn't this being protonated, but this being protonated?
It's delocalized into the benzene ring.
Yes. Take note, this is a benzene ring, right? So it's delocalized, and on top of that, you have your NO2, which is strongly electron withdrawing. It's in fact the strongest electron withdrawing group. So it pulls this lone pair so far away from nitrogen that it's not available already, compared to this, whereby it's not delocalized. Okay, so this is again your ARIO concept, which we'll talk about in the next chapter for basicity. Right. So next page. Esterification, right? This mechanism you already seen before, right? So your carboxylic acid react with your alcohol, you have your ester plus water, right? So now, what are the ways to push the equilibrium towards the right? You already learned to remove water, alright? This is the equilibrium reaction, correct? So one way to favor the ester product is to remove water, right? Another way is, of course, you can use your con H2SO4, which removes water. Another way is you use excess carboxylic acid or your alcohol, which pushes your equilibrium towards the right. Okay? I won't talk about the mechanism, but if you were to look at the mechanism yourself, you'll see that it's again a nucleophilic A-cell substitution. Right? In fact, all the mechanisms in this chapter are nucleophilic A-cell substitution mechanisms. So the next one, nucleophilic substitution with SOCl2 or PCl5 or PX3. Have we written the equation for you? So you can use either set of reagents to perform such a transformation, right? Okay. So write the balance equation for the above reagents. This one I'll leave it to you, right? This one should be covered in your notes as well. Next is a reduction. You can reduce your carboxylic acids to the corresponding alcohols, right? So you have a RCOOH, right? If I reduce it, I'll have my alcohol, right? ROH. And if you were to Google the mechanism, is again a nucleophilic A-cell substitution, right? But we call it a reduction, right? So take note that reduction involves the nucleophilic attack of H-. This one we talked about last week. Carboxylic acids are less electrophilic than carbonyl compounds, thus cannot be reduced by weaker reducing agents like NaBH4. And later on we'll see why they are less electrophilic, right? So just now we talk about carboxylic acids being able to reduce them, but you can actually oxidize carboxylic acids as well, but only a few carboxylic acids, right? The first one is your methanoic acid. If you oxidize your methanoic acid, you will get your carbon dioxide plus water, right? Only these two are for information, right? Another one is your ethanol dioic acid. If you oxidize it, same thing, you'll get CO2 plus H2O, right? You can just go and balance the two equations. Same thing for the one above, right? CO2 and H2O. So, therefore, it's not right to say that no carboxylic acids can be oxidized, right? So let's try this example, okay? word organic, right? Give the structures of the organic products. And you should know that carbon dioxide is not organic. You should have 1, 2, 3, 4, 5 moles of carbon dioxide being produced, right? Let's see, you have this structure, correct? The first step is to break all the double bonds, correct? So break, there are 3. Afterwards, I add O to the 2 ends, which I've broken, O, right? Afterwards, I add OH to the positions here, right? So I have OH here. This is the one of the special structures above. These will eventually be oxidized to carbon dioxide and water. So I can ignore this, right? Correct, so I just put it here, right? Next, same thing for this. I add a OH, I add a OH. Again, these will be oxidized to carbon dioxide and water. They are the same. So I'll be left with this portion. So remember, for this portion I have to add a OH here, right? Since it's under acidified conditions, right? Hydrolysis will happen. This is the ester group. So if I hydrolyze it, right, I will have OH here, and I have OH here, right? Again, this is the special structure above. This is the same as the first one, right? So these will be oxidized to your carbon dioxide and water. So I will have generated 1, 2, 3, 4, 5 CO2, and I'll only be left with this structure which cannot be further oxidized. So therefore my answer is only this. Okay, so you can just do it systematically like this. And the trap here is, remember to hydrolyze the ester bond. Okay. So initially I've thought of giving the oxidative cleavage of beta carotene, right, which is this, right? And I've seen them given this structure before, right? You perform oxidative cleavage on beta carotene and what we will get. So same way to analyze, just break all the bonds, but you have a lot of carbon dioxide, right? I thought of just giving this, right? So this is it for carboxylic acids. Next, carboxylic acid derivatives. Compounds with COX groups where X can be a heteroatom, right? Basically, the important thing is X is a heteroatom, which is not carbon or hydrogen. Boiling points wise, acyl chlorides and esters cannot form intermolecular hydrogen bonds because they don't have hydrogen. And they interact by weak dispersion forces, which is your PD-PD predominantly. Thus, they have lower boiling points than carboxylic acids. Amides can form intermolecular hydrogen bonds, thus have higher boiling points than acyl chlorides and esters, right? But take note, right, of example 6. A lot of people commit this crime. Can the lone pair of nitrogen be used for hydrogen bonding? This is the question, right? So let's say you have this species, RR. We know that there are lone pairs of nitrogen and oxygen. So for oxygen, it's quite obvious that it can form hydrogen bonds with another species, right? But can you draw such a thing or not? The answer is no, right? Remember we talked about delocalization, right? This lone pair is actually delocalized. You have learned in biology, right? Precisely because of this delocalization, that's why you can have your alpha helix, right? That's why you can have your aligned hydrogen bonds, right? Why are they aligned? It's because this part is planar. Imagine if it's crooked, how are you going to hydrogen bond to another of your polypeptide chain above, right? So this is actually planar. In other words, this part is planar, right? You'll learn about it in amides. So once you delocalize, you will generate this species. I believe you have seen this structure in your nitrogen compounds chapter, right? So therefore, because of this delocalization, is not available for hydrogen bonding, and you can only hydrogen bond via the lone pair on oxygen, right? So just take note. Solubility wise, although the derivatives cannot form intermolecular hydrogen bonds, they can form hydrogen bonds with water, which make them soluble, right? Like what we have discussed for carbonyl groups, they can also form hydrogen bonds, but with water only. In other words, they can only act as hydrogen bond acceptors, but not hydrogen bond donors. Unlike your amides, unlike your carboxylic acids, right, which can act as hydrogen bond donors because they have polarized OH bond. Okay. Most acid derivatives other than amides are soluble in organic solvents, right? And for your acyl chloride, it is soluble in water because it reacts with water, right, to form something soluble. The next part is about the reactivity of your acid derivatives, right? Like carboxylic acids, carboxylic acid derivatives also undergo nucleophilic acyl substitution reactions, and the reactivity of your nucleophilic acyl substitution reactions are because of two reasons, right? Same thing, we'll always talk about these two reasons. The first is inductive effect, which is your electronic effect. Recall that your inductive effect is about electronic effect regarding sigma bonds, right? So electron withdrawing groups and electron donating groups exert different effects. Electron withdrawing groups causes the carbonyl carbon to be more nucleophilic, thus encouraging nucleophilic attack and vice versa, right? So I really drawn the relative partial charges there for you. So for the first species, the nucleophile will attack it to a higher rate because it's more electrophilic, right? And if we were to look at the second one, it's actually your resonance effect, right? We have learned the two effects in our intro to organic, that chapter, right? So for inductive effect is via sigma bond, resonance effect is via pi bond, right? Atoms with lone pairs is conjugated to the carbonyl group and is able to delocalize and contribute electron density to the carbonyl group. So for the first box, the box on the left, right? If you compare oxygen and nitrogen, both of them are from the same period, right? Both of them, the orbitals are about the same size because they're from the same period. Both of them involve 2p orbitals. So if you were to look at the bonding picture, you can see that for both of them, the delocalization is quite efficient, but because oxygen is more electronegative than nitrogen, the donation of the electron is less effective. If it's less effective, it makes sense to think that there's a greater delta plus on carbon since it donates less, right? While for nitrogen, since it's less electronegative, it can donate more electrons, the plus is smaller. Therefore, your esters will be more reactive towards nucleophiles than your amides, and that is true, right? Amides are more or less inert, that's why they form your polypeptide chains. Otherwise, they will really denature, right? So now if you compare atoms across different periods, for example, the box on the right, if you compare Cl and OR, overlap of orbitals for Cl will involve the 3p orbitals, but for oxygen it's 2p. We know that the two atoms, right, which is this carbonyl, right, involves 2p and 2p. Now if you introduce something which involves 3p, the overlap will be not as efficient because Cl, if you look at that diagram, is bigger, right? So the overlap is less effective. Since it's less effective, it donates less electron to the carbon, therefore it's more positive, right? Makes sense, huh? And for the right hand side, since the overlap is greater, therefore it donates more electron density, the plus is smaller. Do note that the plus and minus is only relative, so don't compare the left box with the right box, okay? It's just to illustrate the effect. So it makes sense to think that the acid chloride will be more reactive than your ester, right? So after we talk about these two, we can roughly draw the trend in reactivity between these three species. We know that acid chlorides will be more reactive than your esters, which is in turn more reactive than your amides, right? Based on what we have discussed, first is your inductive effect, second is your resonance effect, right? So we only need these two effects. The first one is via sigma bond, the second one is via pi bond. Why do we not talk about steric effect? We always talk about electronic, right? Because these two are electronic effects. Usually we talk about sterics, but for this we don't really talk about sterics, because remember what I say, this is a 120 degrees, so there's not really much of a sterics to begin with, right? So there's no point comparing sterics. Therefore we only focus on electronics, which is because of these two sub-factors, right? So now if both the inductive effect and resonance effect is taken into consideration, we can summarize the reactivity of some common groups, right? Take note that the values are just arbitrary, it's not absolute values, right? So for inductive effect, we know that chlorine, we can say that it's -4, right? Just give it arbitrarily. And for OR is -6. Why do we use a negative sign? Because remember, inductive effect causes it to withdraw electron density from this carbon, right? So therefore we put negative. So for chlorine, OR and NR, all of them are negative because they are more electronegative than carbon. But for R, we just put a positive because R is carbon. Carbon is supposed to be electron donating by the inductive effect, right? So we know that out of these three, oxygen is the most electronegative, so therefore it is the lowest in magnitude, -6, followed by nitrogen and chlorine. Nitrogen and chlorine are about the same in electronegativity, right? So we just give them arbitrarily. R is just +1, right? And then for resonance effect, R, there's no way to resonate, right? Ketones and aldehydes, there's no resonance structures, so we put 0 for R. And for resonance structures, we know that NR, right, your nitrogen is +10, because like what we said, nitrogen, like what we discussed just now, nitrogen is the least electronegative, it can overlap well, so it can donate a lot of electrons. So since it's a donation of electron, we put positive, right? I hope it's not too confusing. And for oxygen, since it's slightly more electronegative than nitrogen, it's less donating, we just put a +8. For chlorine, since the overlap is not effective, we just put a +1, right? So if you just roughly add up the two values, you will see that for nitrogen is +6, O is +2, Cl is -3, R is +1. Okay? This means that if you were to draw the partial positive values, right? Since Cl is -3, in other words, is net electron donating. If it's net electron, is net electron withdrawing. If it's net electron withdrawing, the delta plus will be very, very big. And for OR, since it's net electron donating, this one will be smaller, right? And for amide, it will be even smaller. And then followed by your ester, which is only slightly bigger than, only slightly smaller than your OR, right? So we can have the following trend. Okay. Now this has some interesting implications because we know that for a general nucleophile, you will react with acyl chloride the fastest, right? In fact, this means that if you have all 4 species and we throw in a nucleophile, the nucleophile will of course like to attack this compared to the other 3, right? So generally, right, we have came up with a general trend towards nucleophiles, right? General reactivity, and I already listed that. So the most reactive will be our acid chloride, followed by the center one, right? If you don't know what it is, don't worry, you can ignore it, right? But I should be able to rationalize its reactivity, right? Followed by your aldehyde, followed by your ketone. Aldehydes, remember, are more reactive than your ketones because there's less sterics and there's less electronic effect, and they are of course more reactive than your ester and then your amides, right? This is the general reactivity explained using what we have discussed just now, right? So you can go back and digest it. So now example 7, right? 1 mole of the following molecule is reacted with 2 mole of OH minus, right? Can you change the 2 to 3? Okay, reacted with 3 mole of OH minus. So what is the major product obtained? Right, trust me, if you don't understand reactivity, there's no way for you to do this question. By the way, you only react with 2 of the functional groups, right? Even though I say it's 3 most. So it should be obvious that the first one is the acid chloride, okay? So how come I need 3 moles? The reason is because if you write the balance equation, right? You know that this will be hydrolyzed. This is the organic product. So what about non-organic product? It will be NaCl. Of course plus water. So you'll need 2 equivalents. You can go and balance it, right? So now the last mole of OH minus, where will you attack? You have a few choices, right? You have four choices: amide, ester, and your 2 ketones. You know that it cannot be the amides because it's the least reactive, right? Neither can it be esters if there are ketones present. So the question is, which ketone? The one on top or the one below? And then you recall your carbonyl compounds, right? The one on top is right beside a benzene ring. So it's less reactive than the one below, which is isolated from the benzene ring. because we have learned that the benzene ring will make it less reactive, right? So now you have the answer, right? OH minus will react the aldehyde, will react the ketone under nucleophilic addition reaction, right? We have learned last time, right? But take note, the nucleophilic addition of OH minus to ketone is only for information, right? If let's say it's during the exam, you assume that it's the ester bond that is being broken, right? Because you all have not learned this reaction, right? So in exam, just take note. If you have your aldehyde or ketone together with your ester, right, it's the ester that will be broken, right? So for this case, I'll accept two. One is the one below, right? The one is the ester bond that's being broken, right? So if the ester bond is being broken, you have these species, right? And the other side, okay? And take note, in order to hydrolyze esters, you also need heat. You cannot just throw in acid, right? Although sometimes it might work, right? So please take note. Next, reactions of a carboxylic acid derivatives. If you have an acid chloride, like what I've discussed just now, you can either use water or NaOH to hydrolyze it. There will be white fumes of HCl produced with water, but not NaOH, right? Like what I've written here, because you will get NaCl, right? So take note of what you are using to hydrolyze it, right? This is again a nucleophilic acyl substitution reaction, right? So comparison of ease of hydrolysis. This is that question just now, right? If you compare these three species, the last one will not react. The first one will react the fastest, and the second one will be medium, right? The reason already summarized in this table. For your acyl chloride, carbonyl-carbon is highly electrophilic due to two electron withdrawing groups. But for the alkyl chloride, there's only a single electronegative atom, and for the aryl chloride, because of the partial double bond character, blah blah blah. Same thing, you can use sterics. For acyl chloride, there's less sterics. Alkyl chloride, there's more sterics because it's 109.5. Aryl chloride is the most sterics hindrance, right? Because remember, in order to have an SN2 kind of reaction, it must approach along this axis, right? If it's along this axis, right, it's strictly blocked, so that's why it is not reactive, right? So therefore the reactivity will be highest for acyl chloride and so on. And for reaction with AgNO3, which is a determining test for Cl containing species, it will be the fastest rate for the one on the left, right? Acyl chloride, then aryl chloride. For aryl chloride, there's no precipitate because there's virtually no reaction at the start. Okay. So again, example 8, hydrolysis. This one already given you the answer, right? Suggest which one is hydrolyzed the higher rate. You'll be the one on the left. But if let's say the question asks for which one will produce the highest mass of precipitate after complete hydrolysis, you'll be the one on the right. Because of course bromine is larger, right? So the AgBr will be heavier, of course, right? So if you were to draw this kind of graph, right? Let me see, what should be the label? This is mass of precipitate against time, right? You should have two. One of it is like that. The other one is, how should it be? If let's say this is if this is this. I want to draw the one for the second one. How should I draw it? You can try drawing, right? The second one will be like that. Because its rate of hydrolysis is slower, but I produce higher mass, right? Because AgBr is heavier, right? I believe you have seen such kind of questions, right, the other time. You just take note. So next, esterification of your acyl chloride. This is the way to form esters. Take note, this is the only way to form those kind of esters involving a phenol, right? If you are forming the ester with phenol, you have to use sodium or sodium hydroxide with phenol first to form the phenoxide. You cannot just use phenol, right? Because phenol, remember, you have your lone pair delocalized into your benzene ring, right? So therefore it is less available to do the nucleophilic attack. Because for this you will involve a nucleophilic attack. I'll just abbreviate it with PHOH, right? PH stands for phenol. So this will attack to form this species first, which is your tetrahedral intermediate, right? Take note that this is slow. And for your second step, right, remember it's the loss of a living group. Right, this is exactly the same mechanism. So this will come back down to kick this Cl because this Cl is a good living group. Right? Remember, don't anyhow break your bonds without drawing any arrows. So for example, I never break this OH bond, so this OH bond stays intact all the way. Right? Plus your Cl minus. Right? And the last step will just be this Cl minus taking away this hydrogen to form your ester, right? So example 9 suggests why the addition of the two are necessary, right? This is an A-level question. So same thing is related to your acid base, right? So after you add sodium or your NaOH, you have your phenoxide being generated, right? So this is a stronger nucleophile than your phenol, right? So that's why you need to deprotonate, right? It's because you can first talk about the delocalization of this lone pair into this, right? Which will eventually make it a weaker nucleophile. Therefore, you will need to add Na or your NaOH to deprotonate such that it becomes a stronger nucleophile, right? So remember to talk about the delocalization, leading it to a weaker nucleophile. Therefore, you want to deprotonate and make it a stronger nucleophile, right? So next, formation of amide. If let's say you have this species, right, you can throw in ammonia, right, or amine species to form an amide. The mechanism is the same, right? So with reference to the mechanism just now, I can just change this to a NH3, right? Same thing, NH3 will attack guaiac, and this will form NHH plus. Right, everything is the same. Next step, same thing, this will again kick this out. I just have to change all the species to NH3. The rest are all the same. Again, it is fast. These will become again NHH plus. And the last step is again the same. I just change it to ammonia, right? H. So for the final step again is the deprotonation. I'll have HCl plus NH2. Everything is the same. And just take note, right? For this case, you need an additional base, right? Please take note, this is very, very important. Because remember, you generate HCl and you are adding in the base. So what will happen is the additional base will just neutralize the HCl to form, right, NH4Cl. This one you should know from your secondary school, right? That's why you need an additional mole of base. So when you balance your equation, take note of this as well, right? Also take note that you cannot use the method to form amides from carboxylic acids, right? We have talked about the reactivity trend. We see that your acid chlorides are the most reactive, so that's why they can react in this way. For your esters and your carboxylic acids, they are much less reactive than your acid chloride, so therefore they have different, very, very different reactivity compared to your acid chlorides and cannot react in this way, right? Now the last page, amide hydrolysis, right? So for amides, you can also hydrolyze them. So for example, your proteins whatsoever, you can subject them to hydrolysis conditions, which is your acid plus heat or your base plus heat, right? So you can hydrolyze them and you have the corresponding carboxylate plus your NR2H if it's under basic conditions, right? If it's under acidic conditions, you have your, just protonate the two, right? You have your carboxylic acid plus your H2NR2 plus, right? Plus your ammonia, right? Plus your ammonium. This is under acidic, this is under basic, right? And the mechanism is similar to ester hydrolysis, right? We have talked about ester hydrolysis just now. Next is your amide reduction. For amide reduction, right, you can use your lithium aluminum hydride to reduce it, and what you will get is your corresponding amine, right? Now imagine if, let's say, I give you a question, right? The question is, how do I form this amine? How do I form this amine? Right? Now some people will suggest, okay, I can maybe perform an SN2 with this, and then I'll get my amine, correct? But the problem with SN2 is that it can perform multiple substitutions. After one round, after another round, and eventually I have tetra substituted even, right? So how do I form this kind of amide? Now the best solution is, instead of reacting this with this, I'll react the acid chloride with this. So if I react my acid chloride with this, right, I will obtain this, and then it won't undergo any further reactions, correct? Because now it's an amide, it's delocalized, and it won't attack another species. Afterwards, then I perform reduction, and I'll get my product cleanly, right? So that's why this is one strategy, take note, right? One synthesis strategy to prevent getting an over-substituted amine, right? So now the question is, how do you get from this to this, right? Again, we need to look at the mechanism, right, to decipher how this transformation came about. So this might seem a bit dull, right? But once you understand it, you'll be eureka, right? So same thing like what we always assume, we can just treat lithium aluminum hydride as a H minus, right? So same thing, the first step is a nucleophilic attack, right? That's what you have always encountered. Okay? But now remember, lithium aluminum hydride. After I donate a H minus, I will form AlH3, correct? Because originally it's AlH4 minus, correct? So what will this do is that aluminium likes oxygen very much, right? So what will happen is, instead of just leaving O as O minus, you can actually coordinate to AlH3. Remember, AlH3 only has got 6 electrons, right? So after you coordinate to O, it has got 8 electrons, so it's very happy, right? So you can actually coordinate to this, and of course this must have a minus charge by conservation of charge, right? So you can just write the first equation as this plus your AlH3 to form this, right? Now I just draw from here so I don't have to repeat, right? You can ignore the fast law, right? So now for the second step, right? Remember I talked about which one being a good leaving group, blah blah blah, right? For now, if you compare O and N, right, there's both O, there's O and N, and for both of these there's lone pair. So you can either come back down to kick this N out, or this come back down to kick this O out. And we know that O is more electronegative, so the leaving group which contains O will be more stable. So what will happen now is that this will come back down and kick this O instead of the other way around, right? So after I kick this O, I have this species, and R, and this H, and of course plus the AlH3O minus, right? Plus this species, right? But what is important is this species, And remember, if you add a lithium aluminum hydride, right, what will happen is there is H minus still present in the solution, right? So what you will do is that now you will just undergo a nucleophilic addition mechanism. This is exactly the nucleophilic addition mechanism, but instead of a carbonyl, you have a CN, correct? So what you will do is that you will just attack the CN. This is exactly a nucleophilic addition reaction, right? So you have HH, and you have N, H, and you have R, and you are done. Right? You can ignore the fast flow. Okay, so the first step is just a nucleophilic addition. Nucleophilic acyl substitution, if you call it, and the second step is just a nucleophilic addition. Now what you have learned. So that's how you obtain this product. Right? It might be a bit confusing. next one, ester reduction. Actually, this mechanism you can just find it online, right? It's also available. It's not like I invented it, right? Ester reduction, right? If you have this ester, and if you reduce it using lithium aluminum hydride, right? What will you obtain? Can you still remember? You obtain two alcohols, right? You have this side, the alcohol, and you have the R prime OH. How does this mechanism go is the same, right? If you wish to draw it. But again, this is just for info, right? You have a H minus coming in to do the attack. This is a nucleophilic attack. OR prime, O minus, and a H, right? So now it has got three groups, H, R, and O, R prime. So it can kick out this O, R prime, so that it's more stable, right? So after you kick it out, you will form this group, which is this part, right? Followed by the R prime O minus. The R prime O minus later on will be protonated, and you form this species, right? And remember, this species, this is an aldehyde. If you have H minus, right, it can come in and reduce this. This again a nucleophilic addition reaction, and you should know that aldehyde, when you reduce it, you'll form your eventually you'll form your carboxylic acid, right? And this gets protonated, and it's exactly this species, right? So even if I forget the product, if I draw the mechanism, I can deduce the product, right? So next, remember last time we talked about the Grignard reaction with your esters, with your carbonyl compounds, right? The RMGBr species. They can, since we say that they are nucleophiles, they can also react with your esters or your acyl chlorides. Okay, again, this is for information, right? And you should be able to predict the product. Why do I say so, right? So far we have talked about this thing react with your nucleophile, right? So what will happen is, after this reacts with your nucleophile, you have this species plus your X minus, of course, right? Correct. So now if let's say this nucleophile is still present and it is still nucleophilic enough, it makes sense to think that it can react with this under nucleophilic addition reaction, right? Remember just now this one is a nucleophilic acyl substitution, right? For the second step, it can react with it under a nucleophilic addition reaction such that it forms this species, right? Which you have already learned in the last chapter. So this is exactly what is happening, right? Remember your Grignard reagent, I told you to pretend it to be a R minus, right? So if you react with your nucleophile, this one will become an R, correct? So if you react with it again, the R will just add across the CO, and you have this product, right? So this is the final product that you will get, right? This is the intermediate. You will not isolate this. Okay, I will not dwell on the mechanism because it's exactly the same once again, right? Okay, the last reaction, which is your Claisen condensation, right? Last time we talked about the Aldol reaction, remember? Right, lucky Aldol reaction and the unlucky ones. This is something similar to the Aldol reaction, but it is with respect to your esters, right? It's called condensation because you are eliminating a small ROH molecule. Okay? So for now, we'll skip this example first, right? Because eventually you'll see this question in your prelim practices in the next few pages, right? So we just do some practice for now. Before that, let's go through the true-false questions. So for the first one, carboxylic acids have lower boiling points, which is false. Second one, carboxylic acids are more soluble in base and water, which is true. Next, carboxylic acids do not dimerize in water. They only dimerize in vapor or nonpolar solvents. Metanoic acid is more acidic than ethanoic acid, which is false, right? Because your ethanoic acid has a electron donating alkyl group, while for metanoic acid there's only a hydrogen. Carboxylic acid can react with sodium bicarbonate, which is true, right? This is called bicarbonate. The other one, which is Na2CO3, is called carbonate. Next, H2O is more acid than H2S, which is false, right? Because by aerial rule, size dominates. The right hydrogen has a lower pKa, which is true because of the orbital effect. Carboxylic acid derivatives react in the same way as carbonyl compounds, which is false. Carboxylic acids undergo substitution, carbonyl undergoes addition. Carboxylic acid derivatives undergo nucleophile substitution reactions, which can be classified as SN1 or SN2, which is false, right? They proceed by a different type. Amines undergo nucleophile substitution more readily than, amides undergo, which is false, right? Esters are more reactive. We have seen from the trend. Hydrolysis of nitrile in basic conditions can generate carboxylic acid, which is false. They can only generate carboxylate. And carboxylic acids do not react with 2,4 pH. The answer is false, right? It should be no observation. It's not do not react. Okay? Hydrolysis of acyl halides and esters require the same conditions, which is false, right? If you want to hydrolyze acyl halide, you can just add H2O. But I can't do that for esters. You need heat and acid or base, right? Amides can be formed by the reaction of carboxylic acids and amines, which is false, because you only generate the salt, right? PCl5 can be used to distinguish alcohols and carboxylic acids, which is false, right? Both can react. Next, carboxylic acid can be reduced by lithium aluminum hydride, which is false, right? Remember, lithium aluminum hydride must be in dry ether, cannot be aqueous, right? If you use aqueous, you are destroying the lithium aluminum hydride. And next, no carboxylic acids can be oxidized, which is false. We already seen 2. Amides cannot form hydrogen bonds because the nitrogen lone pair is delocalized, right? Esters are more reactive than ketones, which is false. Ketones are more reactive. Remember, esters have OR, which is net electron donating, right? And the molecule on the right is hydrolyzed at a higher rate, which is false. The one on the left, because Cl is more electronegative. And acidification of phenol can be achieved by direct addition of acyl halide, which is false. You need sodium or NaOH to activate it, right? So now let's try the practices. By the way, next week I'm going Malaysia, right? Saturday, Sunday. When's your midterms?
After drill house.
Yeah, the draw.
Remember, only move down your aerial, that ladder, if the previous one cannot help you distinguish, right? for the first one, what's your answer? D and B. Right? So we look at atom. Atom can't really determine anything, right? Because everything is on carbon. Next, we look at resonance, right? So we deprotonate all these species and we see which one can resonate. All of these four, only A, B, and C can resonate. D, there's no way for it to resonate, right? Because if you deprotonate D, this is what you will get. Right? There's no way for you to draw any resonance structures. Remember, in order to draw resonance structures, you need to be beside or one bond away from a double or a triple bond, right? So for example, like this case or like this case, then you can resonate, right? So D cannot, which means D is out. You only have A, B, and C, right? So since A, B, and C all can resonate, then we look at which one can resonate the best, right? And if you look at B, you can see that for B, it can actually delocalize into the CO and the CC, right? You have a CC here and a CO here. If you have a negative charge here, you can delocalize into either one, right? Because it's one bond away. Okay, so this is CO and CC. If you look at A, right? Same thing, you can delocalize into a CO and a CN, correct? CN is something like a CO, like what I told you the other time, right? No matter it's C something, as long as it's a double or triple bond, right? It's more or less the same. That's for A. If you look at C, for C, you can delocalize into either the left, the one on top, CO, or the one facing below, the CO, right? So now we are comparing delocalization between two COs, one CO, one CN, and one CO and one CC. And if you recall from what we have learned just now, O is more electronegative, correct? So delocalizing to a 2CO will be more stable. So therefore, C will be the most acidic, right? This is making use of A real rules, right? And then for question 2, I'll just go through question 2, right? Because it seems that a lot of students will struggle with second one, right? So the question is, why we need to learn nucleophilic A cell substitution? Why we can't just, let's say, perform a SN2, right? For example, SN2 is just like that, correct? Which is much simpler. Why do we have to go up and then later come back down, blah blah blah? And then we have to ask ourselves, what favors SN1 and what favors SN2 once again, right? So we know that for SN2 it involves the backside approach, and you will need to have a pentavalent transition state. That is for the typical kind of SN2, right? So now if let's say we have this structure and we have a backside approach, right? And we generate the intermediate, the transition state. Am I right to say that a transition state will look like this? Correct, right? What's the bond angle of this? They must be 90 degrees. 90, this means that all are 90, right? Compared to our pentavalent transition state. For pentavalent, although yes, there's 5 things connected to it, and this there's 4, but for this there is 90 degrees and there's 120 degrees, which is much more stable than this. In fact, you are forcing the carbon, which prefers to be tetrahedral, to be a square planar shape, right? So this is very, very unfavorable, right? So that's why it's not likely to undergo SN2 mechanism, right? This is for B. Because transition state is square planar and highly unstable. Now, what about SN1? For SN1, you need the X to leave first, right? If you make the X leave, this is what you'll get. You agree, right? A carbocat ion, although it looks weird, right? We call it an acyl cation, right? Now remember, what is actually stabilizing your carbocation for your SN1 is actually the electron donating groups beside it, correct? But for this case, you have an electron withdrawing oxygen group that's actually beside it, right? And apart from that, usually all those carbocations that we see are sp2 hybridized. In other words, right, for example, the SN1 case, we have this positive charge lying in the unhybridized p orbital. And remember, last time I told you what actually stabilizes this is actually the CH bond that is actually eclipsing this and donating electron density. And I say that this is hyperconjugation. Remember the term, right? This is what's stabilizing it. But for this case, do you think it's lying in the unhybridized p orbital? The answer is no. It's actually lying in a, you call it a sp2 orbital, right? If you wish to call it. So it's actually pointing away from these two atoms, and there's no way for you to overlap sideways to stabilize it, right? So you can use either ways to explain. The first is that this positive charge lying on this carbon, so this oxygen, which is electronegative, withdraws it, destabilizes it. This is one way. Another way is you use this to explain, which is more chin, right? Depending on which way you prefer. But either ways, you should see that it disfavors SN1 kind of reaction. So it doesn't react via either ways. Okay, Let's try question 4 first, right? I think 4 is more interesting. First one, okay, you should have a acid-base product, right? Because you have your carboxylic acid reacting with your amine, so you will have acid-base reaction, right? This one we already learned. So you can either protonate the amine on A or the amine on B or both, right? Since I never specify how many equivalents. So your answer should be either this H2N plus or this, right? Yeah. get a bicyclic structure, right? So now the difference is just I'm changing this to Cl, right? So you should know that this product is unstable. Remember, in order to form amide, we have learned just now that you need to react acid chloride with your amine, right? But there's an internal amine here. So what will happen is you just form an internal amide, right? So you have to draw the structure properly, and that's the answer, right? And why doesn't it form an amide? Because intramolecular reaction is always faster than intermolecular because of the entropy factor, right? It's closer. Okay. And remember, you will lose hydrogen when you bond to the thing, bond to the Cl, right? So if you have this plus NH3, you lose a hydrogen, right? Because it become NH2 plus HCl, and you need two equivalents because the other one will form NH3Cl, NH4Cl, right? So for B part 1, right, you know what's going on, right? One of them the rate is slow, one of them the rate is fast, right? So like what we discussed just now, for the one which the rate is fast means that it must be more electrophilic, right? If you compare the two reagents, the only thing that's different is one of them is nitrogen, one of them is carbon, right? So what's the implication of this? One of them is like that, the other one is like that, right? It's actually quite simple. Don't have to think so hard, right? The concept is actually very, very simple. This is nitrogen, correct? So we know that in order to form the product, it must attack this carbon and somehow kick this thing out. I'm not asking for the mechanism anyways, right? So it means that the more positive it is at this carbon, the more likely it is to attack, and the higher rate the reaction, right? So comparing these two, for this one is a nitrogen, this is electron, is electronegative, so it actually pulls electron density. But for this, there's a carbon, so it actually donates electron density, right? So if this pulls electron density, this lone pair, right, which we discussed just now, by the resonance effect, will donate less, and by the inductive effect, it will donate less as well, right? Therefore, this will be more positive. For this case, it donates to oxygen, so the inductive effect donates more. The resonance effect also donates more, so this one will become smaller in terms of delta plus, right? So therefore, the rate will be higher for root A because it's higher in electrophilicity, right?
Can you also see like this part is less stable?
Which part?
Like when this part breaks off, it's less weight, it's more stable.
It's more stable, also can, right? Because the negative charge is stabilized by the nitrogen, right? That's another good way to explain, right? That's why root A is the one with a faster rate, right? And then for part 2, right, I told you that D can be synthesized from the corresponding carboxylic acid and reagent X in a nucleophilic addition reaction. So this one should be something you know because it's nucleophilic addition, right? And then I ask you to draw the structure of X and describe the mechanism involved. right? So try to think of X C4H6N2. So if you try an error, also not a lot, right? I think. So what's the first step? First step is to do the double bond equivalence thing, right? So how many double bonds or rings? Three, right? Yeah. So 4 times 2 plus 2 minus 6 plus 2 divided by 2, you'll get 3. Okay, I say again, 4 times 2 plus 2 minus 6, 8, 10 minus 6 plus 2 divided by 2. Right, this is the double bond equivalent. You have 3, right? Means that there will be 1 ring plus 2 double bond, or you know. Yeah, I told you that it's a nucleophilic addition, right? Let me give you a hint, right? There's a triple bond somewhere. So it must be a triple bond plus a ring, right? Since it's 3. So it's actually this species, right? Is it? Let me count 1, 2, 3, 4. 1, 2, 3, 4, 6. Sorry. Wait now. This one. Right. Okay. This one's supposed to be linear, by the way, because it's SP. So it's. I don't know how you're going to draw it in linear form. 1, 2, 3. How do you draw 3? 1, 2, 3. Yeah, like that. Okay. Why do I say it's a nucleophilic addition? It's actually very straightforward, right? Remember what I told you? No matter if it's a CO single bond, CO double bond, CN single bond, no matter if it's a CN double bond or CO double bond, the mechanism is the same, right? Remember you have this carboxylic acid. You can just treat this CN double bond as a CO double bond. So what you do is a nucleophilic addition, right? So after this nucleophilic addition, you have this nitrogen. Here will still be, I just draw it like that. Sometimes it's hard to draw. Nitrogen, and you have the other part of the ring, and you have your O, and your OH. Correct? You learn this before, right? This is your nucleophilic addition. The next step is just a acid base, isn't it? So acid base, and you have the product. That's all. Right. It's a nucleophilic addition reaction, just that it's a CN. Right. Nothing much about it. So please be insightful. Don't always just memorize it as carbonyl compounds, right?